Hello and welcome back, everybody. Today in calculus, we are looking at the things that we can do with parametric equations via calculus. So, this is going to be broken into two parts. So basically, the idea is that if you have a parametric equations, what are the calculus applications that you can apply to it? And this is thinking back to first semester. Like say, if you're given a curve, what is it that you can do in calculus? So basically things like solving for the equation of tangent line, finding the area under the curve, and that kind of stuff, right? So let's go ahead and dive into it. So here we have a list of things that we're going to apply to our parametric equations then. So the first one is finding the equation of the tangent line via the first derivative. So that right there again is calculus 1 section right here. So if we're given the parametric equation, how do you find the equation of the tangent line then? And then, with the parametric equation. Then the second one afterward is also find out where is it that you have a horizontal and vertical tangent line with the parametric equation. So again, calculus 1 stuff. Next, we're going to look at the concavity via the second derivative with those parametric equations. Afterwards, the area under the curve of the parametric equation, and finally the length of the curve via the parametric equation. So those are the five, part one of the applications in this case. Okay, so here let's go ahead and look underneath right here for this problem here. Given that the parametric equation is going to be the equation x is equal to ln of t, and also y is equal to t squared plus t, I want to find the following then. The first part is I want to find the equation of the tangent line at t is equal to 1. So over here on the right hand side, you can see that I actually have the graph of it over there, and it's a little hard to see because I have to like squeeze the picture in there, but hopefully you can get an idea as to this. Okay, so the parametric equation is over here, and what I like to do is, again, like I said, find the parametric equation at t is equal to 1. Now in terms of the location, just for our information, let's go and see where that coordinate is. So when t is equal to 1, then that means that x is going to be equal to ln of 1, so that's equal to 0. And then y is going to be equal to 1 squared plus 1, which is equal to 2. So over here, graphically, you can see, hopefully, that it goes through the point 0, 2 over here. And then from there, we're going to find the equation of the tangent line that's over here. So let's think about the, strategies or the ways that we did it back in Calc 1 then. We need to basically solve for what is dy dx, meaning the derivative of y with respect to x. But the problem here is that we have x in terms of t and also y is in terms of t. Now, is it possible so that you can combine x and y together to get rid of t? The answer is yes, but we don't want to do that because that takes a long time. So we need to try to find a better way to solve for it. So here's where we're going to do that instead. We're going to solve for each derivative respectively. So that is to say, I'm going to go ahead and solve for dx dt. And that easily we can do because the derivative of x with respect to t is just going to be 1 over t then. And similarly, if I solve for dy dt, then that is going to give us 2t plus 1. So that part is easy enough. The question is then, well, if we're given these two right now, or if we solve for these two, how do we get to this guy? Well, that's just a simple division then, because if you look at it carefully, dy dx, which is what we're trying to solve for, is going to be dy dt divided by dx dt. Algebraically, they should work out like that then. So put it together, dy dt, that is going to be 2t plus 1, and then divided by dx dt, which is going to be 1 over t. And if we clean up that equation, then we're going to get 2t squared and then plus t then as a result, because the reciprocal of the reciprocal is just multiplying. Now note over here that t cannot equal to 0, so hopefully that should be okay with you because you'll notice that t is in the denominator over here. But I think in this case our parametric equation is going to be okay because for one thing, t can't equal to 0 because of the x is equal to ln of t, and usually t represents time. So I think that part will be okay. Now, I want to find out what is the equation of the tangent line at t is equal to 1. So for what we solve for right there, we're going to go ahead and now apply t is equal to 1 then. So plug that in literally. So dy dx is going to be equal to, when t is equal to 1, looks like it's going to be 2 plus 1, and that is equal to 3. So we have our slope, and now we need the coordinate. So the coordinate we actually solved for earlier because remember, if you remember, we actually did it over here. The coordinate is going to be 0, comma 2. So we got everything we need then. We have the slope, we have the point. We can now go ahead and put into our point slope form to get our equation. So finally, it's going to be y minus 2 is equal to 3 multiplied by x minus 0 in this case. And you don't have to write this in a parametric form because there are technically infinite numbers of answers or parametric equations that can satisfy this condition. So just the tangent line will be suitable. All right, next, let's go ahead and talk about determine if the parametric equation contains any horizontal and vertical tangent lines. So again, let's go ahead and refer back to the derivative part, right? So as of right now, we know that dy dt is equal to 1 over t, and actually, I'm sorry, I think I messed up on that one. Oops, sorry, yes, you're right. Dy dt is going to be equal to 2t plus 1, whereas dx dt is supposed to be equal to 1 over t. And when we combine them together for dy dx, that is going to give us 2t plus 1 divided by 1 over t. Now, if I'm solving for the horizontal tangent, right, the horizontal tangent, that is to indicate that the slope is equal to 0. So that means that if I set the top part over here, dy dt equal to 0, that will allow me to get the horizontal part. And similarly, if I want the vertical tangent, that means that the bottom part over here is going to give me, is supposedly equal to 0. And that is going to now give me the vertical tangent then. So the top, once again, is the horizontal because that's when you get equal to 0 as a slope. But whereas if you have a vertical tangent, then that means that the fraction is going to be undefined. So the bottom is going to be equal to 0 then. So that is easily enough to solve for. We can figure out what t is in each case. So in the first one, we can solve for t over here. It looks like that t is equal to negative 1/2. But if you remember for our problem, t is actually greater than 0 because of the fact that x is equal to ln of t. So therefore, that is an extraneous solution, so we're going to negate it then. And over here, if I'm solving for the vertical tangent line, then I'm going to set dx dt equal to 0. And unfortunately, in this case, we cannot solve for t because if we multiply t to the other side, you get 1 is equal to 0. So there is none over there also. So therefore, in conclusion, there are no horizontal or vertical tangents then. Okay. And if there are, we can definitely solve for it by solving for the t value and then plugging it back like we did like we would normally back in calculus 1. Okay, let's keep going. For this next part over here, what I want to do is solve for the second derivative, which is denoted as d squared y over dx squared, and use it to determine at the curve, for the curve, if at t is equal to 1 is going to be concave up or concave down. So if you remember, yes, the second derivative deals with concavity, and that's what I'd like to solve for. I want to know, is it going to be concave up or concave down over there? Now, once again, let me go ahead and write the second derivative, which is, again, written in the form of d squared y divided by dx squared. So another way of thinking about it is that the reason why it's in this notation is that you are taking the derivative and then you are taking the derivative and taking its derivative with respect to x. Now, this I have because we already solved for it. That right there, if you remember, we just solved for it earlier, is supposed to be equal to 2t squared plus t. So that's kind of nice. But the problem is the equation on the right-hand side is with respect to t. So that means I can't take the derivative with respect to x. But let's do a little bit of algebra manipulation so then we can kind of, I guess, work around it. So here, what I'm going to do is I'm going to go ahead and say d dx. And now what I'm going to do is I am going to, multiply and top and bottom by something over here. Let's see if I remember how this is going to be done. I am going to sneak in, sorry, I'm getting a little bit of brain fart over here. If I have dx over wait, shoot. How does it work? Here we go. Now I remember. Sorry about that. There's a little bit of delay. Let me go ahead and multiply by dt over dt, okay? And then we still have dy dx over here, okay? And if you're thinking, okay, well, what is that going to do? Well, let me go ahead and switch some of these terms around so you can see what's actually happening. If I move some of these terms around, I'm going to get d over dt, and then I'm going to have dx over dt, and then sorry, not dx over dt. It should be dt over dx. Yes, that's it. So dt over dx, and then of dy dt. So all I did was just kind of switch some stuff around so I can introduce the derivative of t. Now here's the magical part. So let's go ahead and put the first two together so you can see now, hey, look, there, I am going to take the derivative of dy dx now with respect to t, which is what I want. And then for this part right here, notice that the notation is dt dx. Well, another way to write that is dx dt in the denominator. So right there, that's how we're going to solve for the second derivative then. So here, it's basically saying that I am going to take the derivative of dy dx with respect to t, and then divide that by the current derivative of dx dt right there. All of those we can easily do, hopefully. So here, let's go ahead and write that out. So the derivative of respect to t of dy dt, dy dx, that is the derivative of 2t squared plus t. And then divide by dx dt, remember we solved for that. That is supposed to be 1 over t, right? Earlier, we solved for it once again over here quite a bit of a time because x is equal to ln of t. Okay, so now it's just a matter of cleaning this up. So the top part, the derivative of that is going to be equal to 4t plus 1. And then the bottom part, once again, it's going to be 1 over t. And note that once again, t cannot equal to 0, but I think it's going to be okay in this case. And if we now take the reciprocal of the bottom, then we get 4t squared plus t as a result. Now we're going to go ahead and plug in t is equal to 1 because I want to find out what's the concavity over there. So it looks like numerically, this is going to be equal to 5, which tells me, therefore, this is going to be concave up in this case because the second derivative is positive. And if you look at the graph right there, you can see that at this point where, remember, t is equal to 1, yeah, it is concave up because of the way that it is drawn in the picture according to the graph. Okay. All right. So hopefully all of that isn't too bad so far. Next, now I wanted to, this is closing to the end. What I want to do now is I want to find the area under the curve of the parametric equation of x is equal to ln of t and y is equal to t squared plus t for values of t that's between 1 to 4. So somewhere over here, right, if you remember, that's when t is equal to 1. So here, t is equal to 1, and somewhere over here is for t is equal to 4. And I want to find the area under the curve of that portion that is located over here. Okay, you should note that for my graph, technically it's a little bit bigger because if you look at the parameter that I set up so that's t from 0 to 5. So technically t can go on to infinity, but we're only going to fit in just the small part right now. But anyhow, for part D over here, I want to find the area under the curve from from t is equal to 1 to 4. Now, let's think about how this actually works out first. First and foremost, it is very important that you should note that this method right here can only be applied to the parametric equation if the parametric equation itself is a function. So meaning that if I have a parametric equation that overlaps like this, then that is not a function because that is a relation. And so therefore, I can't technically find the area under the curve. So it is important that that has to be true first, which in this case it is. If it's, again, the case where it is not an equation, if your parametric equation is not a function, then we can't apply this. All right, so now let's think about what we did in calculus in order to figure out what this is. The area under the curve, right? The area under the curve, A, B, C, whatever you want to call it, is so normally from A to B of y dx, right? Because that is, the area under the curve. It's like literally base times height. Well, all of those things we actually have, so we can actually apply to this. Y, we know the equation for. Y is supposed to be t squared plus t. And then dx, well, if that's what you're wondering what that is, we can solve for it over here. So what's going to happen is the area that I'm looking for, I'm going to change it so that everything is in terms of t. So you can see how that works out. So here we go. The integral, we'll set up the boundary right now, or actually in a little bit. Y, first of all, that's going to be t squared plus t because that's just y. Dx, well, if x is equal to ln of t, then that means that dx is going to be equal to 1 over t dt. So that is going to be my replacement over here. And since everything is in terms of t, then my boundary is according to what I want to solve for, which is from 1 to 4. So clean this up, and then we can hopefully solve for it then. The integral from 1 to 4, and then we're going to go ahead and divide through. So we get t plus 1 dt, and that seems like an easy enough integral to solve for. So 1/2 t squared plus t boundary from 1 to 4. Upper bound minus the lower bound after we take the antiderivative. So the upper bound minus the lower bound, so it's 1/2 multiplied by 16 minus 1 because it's 4 squared minus 1 squared. And then we have plus 4 minus 1. So cleaning that up, looks like it's going to be 15 over 2 and then plus 3. So that is going to be our final answer. And if we want to put it together, that is the same thing as saying 10.5 then. Okay. All right. So here's the last part. I want to find now the arc length, or basically the length of the curve from t is equal to 1 all the way to t is equal to 4. So basically here, if I were to kind of like sketch it out on the side, I want to know what is that length from t is equal to 1 all the way to t is equal to 4 equal to. Okay. Now this is something that we have to use the arc length for. And for those of you guys that don't remember it, here's what we're going to do. We're going to quickly kind of like derive it on the side. What we'll do is we'll look at a small little increment piece over here, which we'll call delta S. That length, if you close it, if you make it small enough, then it basically looks like it's a tangent. And what we can do then is create a right triangle where the bottom part is going to be called delta X and the top part is going to be delta Y because it's the change of X and the change of Y. Delta S is going to be equal to the square root of delta X squared plus delta Y quantity squared. So right there, that will basically give us the length of that, that'll give us the length of that arc length. And let's see, now I'm going to go ahead and clean this up a little bit if it's okay. In terms of how do we apply to this? Well, let's go ahead and, well, supposedly, if we take the summation of every single one of those pieces, then that would then give us the arc length that we want. But the problem is we need delta something onto the other side. So then that way we have a summation and also a delta in order to change it into an integral. So the trick over here is, let me go ahead and do it algebraically. Let's go ahead and take this part over here, what I'm trying to solve for. And I am going to divide both sides by delta t squared. And then over here also by delta t squared. Okay. Because I divide by delta t squared, then that means I need to multiply by delta t squared. And if we now clean that up a little bit, then hey, that actually looks pretty nice because delta t x over delta t, that is dx dt quantity squared. And then plus delta y over delta t squared, that is going to be dy dt quantity squared. And then if we take the delta t squared outside the square root, then that's where your delta t is going to come from. So that right there now is going to give us our arc length then. So pulling it all back up over here, the length that we're looking for is supposed to be, according to what we just said, is going to be the integral of the square root of dx dt quantity squared plus dy dt quantity squared, and then we have delta t on the outside. And then the boundary, well, it's going to be from some value to some value. I think we have everything that we need then. So let's go ahead and finish it off. The integral from 1 to 4, because those are my values of t's. And then the square root of dx dt squared. So that is going to be equal to 1 over t quantity squared. Plus dy dt squared, that is equal to 2t plus 1 quantity squared, and then dt. Now, for something like this, unfortunately, a lot of the times we're only going to be able to set it up, and then afterwards you have to use finite integration to actually solve for this. So if you're asked to just set it up, this is as far as you go. But if you do need to solve for it, then we're going to go ahead and throw it into the calculator. to see what we get then. So let me go ahead and do that quickly on the side over here. We have 1 over x and then quantity squared. And then we have plus, let's see, 2x plus 1 quantity squared. And all of that is now going to be inside the square root. So let's see, invisible and then square root. Oops, looks like I'm going to have to put that in there. So let's see, 1 divided by x squared, and then plus 2x plus 1 quantity squared. And I'm going to have to erase all of this stuff. So sorry about that. Looks like I'm kind of taking a little bit more time than I would like. Almost done. Just a small little technical difficulty here, and there we go. And that's going to be in terms of t. So writing it all down, so just saving you a little bit of time. So this, according to finite integration, is going to be equal to approximately 18.086 then as a result. Okay. All right, so there you go. That's going to be our answer. And thank you so much for watching. I will see you guys next time then. Goodbye.